So today I'm going to be talking about things related to concurrency. And the first part is I want to talk about our concept of named workers. And the idea of named workers is that they provide a way of expressing concurrency that can be shown as a sequence diagram. So one of the big ideas in Ballerina is that we want to be able to have a graphical view of a program that gives some real insight. It's not insight into what the program is doing. It's not just a syntax tree. It actually provides you with a really deep, useful view of what's going on. And as I mentioned at the beginning of part 2, there are really three things we're focusing on. There's data, there's network interaction, and there's concurrency. And for the last two, network interaction, concurrency, the experience in WSO2 is that the kind of diagram that works best for that is a sequence diagram. For data, you really want something else, and you really want more of a data flow approach. But for concurrency and a network interaction, sequence diagrams work well. So the basic idea of our main concurrency feature is that it maps onto sequence diagrams. So in this little function here, usually in a function you don't see any of these worker declarations. Everything executes on one logical thread of control. With workers, the idea is you can have multiple named workers. These have the worker and then there's the name of the worker. And these named workers execute in parallel. And they execute in parallel, they execute concurrently with the normal code in the function. So the way this executes is, first of all, you have everything before any workers, before any of the worker declarations. That initiates first. That's the initialization stage, and that executes as part of the functions worker. And then the rest executes in concurrently. So you have worker A executing concurrently, worker B executing concurrently, and those two execute concurrently with the function's main worker. And variables that you declare, if you declare a variable here, or you have a parameter here, then that is accessible to these two workers. So how does that map onto a sequence diagram? Basically, a function can be viewed as a sequence diagram. Each worker in the function has a vertical line. You've got a lifeline for each worker. You have a lifeline for the function worker and a lifeline for each named worker. And this also combines with our concept of client objects. You'll remember that we have this concept of a client object, and we have a different syntax for making remote calls to client objects. So the way that shows up in the sequence diagram is that you have for each client object that you put in this section here, you get a lifeline, and then when you make a call to that client object, that is represented as an arrow from the lifeline for the worker or the default worker to the lifeline for the client. So workers don't automatically, each worker's thread of control does not automatically terminate when the function terminates. They're completely independent threads of control. So when you start a worker, it keeps on tracking until you wait for it. So if you actually want to wait for a worker to finish before you return from the function, then you have to explicitly wait for it. And you do that using wait. So in this case, we'd initialize, then worker A would execute concurrently with this, and this would then wait for worker A. So we have this concept of a strand. So I talked about threads, but we actually have a concept of a strand, which is a logical thread of control. So there's what named workers are about is expressing the logic of your program in a natural way. How that actually maps onto the implementation onto physical strands on your CPU is a separate issue. By default, we schedule named workers in a cooperative way rather than being preemptive. And the reason to do this is to avoid, so you'll actually, if you have multiple named workers, you don't say anything, they will all run on the same thread, and they will only switch, so they'll work more like coroutines. You'll only switch between strands at specific yield points, like doing a wait or when your library function does a blocking system call. And the reason for that is to avoid users having to get into locking variables. So they're not going to get all sorts of nasty data race conditions by default. And there's an annotation that you can use if you really know what you're doing. There's an annotation that you can use to make a strand run on a separate thread, to make a worker, the strand for a worker run on a separate thread. And so when we say strand, that's the word we use to mean logical thread of control, which may be a thread or may not be a thread, depending on the annotations and how it's used. So workers have return values. And by default, just as with functions, the return value of a worker is nil. So in this case, we've declared a worker with return value of int or error. And then we do a check here, and that check may fail. And if that check fails, then the worker will return an error. And then when I wait for a worker, I get its return value. And because that may be an error, I'm checking to see if it's an error. So when I return from the worker, it returns a value from the worker. This gets the return value from the worker, and that may be an error. If that's an error, then I do check, and that will return from the function. So as well as just a simple wait where you wait for one worker, you can wait for a choice of workers. We call that alternate wait. So suppose you have a function that goes fetch some string from some URL, and it may succeed or fail. And I've got two possible URLs I can fetch it from. So I can have two workers, worker A and worker B. One goes to fetch it from URL A, one goes to fetch from URL B, and then I wait until one of them succeeds. And this will return the string from whichever was the first one to return a non-error value. If they both return an error value, then I'll get an error. We also have multiple wait, so you can wait for all. So this waits for one of a number of workers to complete. You're also able to wait for all of a number of workers to complete. So here we have, we have a record that represents two results, each of which can be a string or an error. And we're going to go fetch from two URLs as before. And this time we want all of them, so we're going to return the result from URL L in A and the result from URL B in the B field. So we've got two workers, worker A, worker B. We fetch them. Worker A fetches from URL A, worker B fetches from URL B. And here we do this special thing, which looks like a record constructor. And this is actually a multiple wait. What this does is it waits for A and it waits for B, packages the result in a record and returns it. So this puts the result of worker A, which is a string or error in field A, result of worker B, which is a string or error in field B, and returns a field with turns a record with an A field and a B field, as declared in the result. And there's actually a shorthand for this, just as with binding patterns and record constructors, you can say, you can put curly brackets XY, and that's short for X colon X, Y colon Y. And that works with wait as well. And you can also do this with futures, just as with named workers. So we can use wait. All these wait things work both with futures and named workers. And in fact, the reason it works is because they're the same thing. So what is, when we say start, what is that really doing? What start is really doing, it's just sugar for calling a function, which, so let's look at this example here. So we've got a worker which has a return value of int. And this is the interesting bit here. We're using return A. We're referring to this named worker as a value. And what happens is when you refer to a named value as a worker, it turns into a future where the type of the future is the return value of the worker. So this is exactly when you do start on a function, it's just wrapping a little worker, calling a function and not waiting for it. Yes, does this help at all? So here we're calling, yeah, so this is just explaining how start works. You can create a function and start it and return that function. Yeah, so what's quite nice is that we saw the familiar start thing, but that start thing is just sugar for our fundamental concurrency primitive, which is named workers. So I said that named workers, the idea of named workers was that they you could represent them as a sequence diagram. And when you have two lifelines, you want to have, you've got your two vertical lines, and you want to have your horizontal lines. So the way you get your horizontal lines is you can send messages between workers. So in this case, we are sending 1, an integer, to worker B. We're sending 2 to worker C. And then here we are receiving an integer from A. And then this sends it to, we use function to refer to the functions worker. So we're receiving an int from A, and then we're sending it to the functions worker. We're receiving an int from B and sending it to the functions worker. And then here we're receiving something from B, and we're receiving something from C, and we're adding them together and returning it from the function. So ideally I would have a little picture here, but that it doesn't actually quite. Anyway, at one point this worked that you could actually see a picture of this, and it will work very soon again. But you can actually see this. The reason you have, what I think is important here is that important to understand is that these things are matched up at compile time. So at compile time, when I have a send to B, I check at compile time that this and this matches up. Similarly, I check at compile time that this and this match up, and that this and this match up, and that this and this match up, and that this and this match up. And that compile time matching allows me to connect, to draw a line. When you're drawing a line, you've got to draw it from and to, and matching these things up at compile time is what allows you to draw the horizontal lines on the sequence diagram. So this gives you a really nice graphical model, but it does have limited because you've got to do this. It's a plus and minus. You get this really nice. Then everything's checked for you. You can't get deadlocks. You can't get messages that won't be received. You can't receive any. Receive is guaranteed to work. Any send is guaranteed to work. And if this fits what you want to do, this is a really nice way to do it. But there's some things you cannot express with that. So in future versions, hopefully we'll be able to extend this to be a bit more expressive while still having all the nice checking and graphical, and the nice graphical model that we get here. So when you're writing a real function, something may go wrong. So in worker A, I may need to call some function foo, and that may return an error, or anything may panic. So when you're pairing up sends and receives, that's pairing up on the assumption that the worker didn't panic and didn't fail, so didn't have a check fail. So what happens if there is a check fail? Okay, if there is a check fail, then when I try and read, suppose I'd now say I've got a, so this here is paired up with this here. But what happens if this check returns an error? This won't ever get executed. So to make this all work, what we have this concept of error propagation. So if I try to read from A, but actually A failed, I will get the error or panic that caused A to fail. So if this here returned, if this failed with some error, then when I read here, I will get that error. And that's to ensure that, so we have to do it like this, because if you're doing anything useful in a worker, you may get a panic, you may get a failure, and we can't just have those failures disappear into a black hole. We have to get them back. And so they come back here and they're not lost. This means you need to think a little bit about when you're reading. So when you're reading here, we actually compute what are the possible failures that could happen before this. And then that will be the type of this expression will depend, the errors that you get in this type will depend on the possible check fails that could happen here. Okay, transactions. So this is another aspect of, transactions all about concurrency. So this is another part of Ballerina's concurrency story. So it's important to understand what the language support for transactions is doing. What it's doing is providing you with support in the language for interacting with a transaction manager. So like you can do with the Java, I think it's called JDA, something like that, but we do it in a nicer way. We make it nicer by providing language support. So this is not transactional memory. So often when people talk about transactional languages, they're talking about languages that have transactional memory. And what transactional memory is, it's if you do something rollback, then the memory, the state of your memory gets automatically restored to what it was before. That's a very different thing from what we're doing here. So the basic concept is the Ballerina runtime. It includes a transaction manager. We provide language syntax for delimiting transactions. Delimiting transactions means every transaction has a begin, starts with a begin, and the other side of it, it has a commit or a rollback. So we have language support for doing that. And we have a current transaction as part of the context of a strand. And the other important thing is that this composes with our network features. So we have network interaction features, and we have transaction features. And when you put the two together, you get distributed transactions. So in the transaction statement, we have a transaction block here. We do two things. We're doing something together. We want it to be a transaction. We want these to be done together or fail. Key point is, syntactically, is that you have to be explicit about the commit. So you actually have this commit statement. Second point is that commits can fail, and it's a normal thing for commits can fail. So in keeping with the philosophy of Ballerina, that needs to be expressed as an error, and we need to deal with it. Typically, you deal with it by doing check and passing it back. So you can't just say commit and not put anything there and hope it works. We force you, as usual, not to ignore errors and to decide what you're going to do to it, even if that is only passing it back. So what we have here is we have a compile time. We have a compile time guarantee that you're through the syntax and the compile time checking. We guarantee that every transaction is bracketed with begin, and we have a commit at the end. Now, to make this work, we have to extend what I've told you about check. Up to now isn't quite the whole story. I've explained check as when it fails, it returns from the function, returns an error from the function. This isn't the whole truth. When a check expression, when the expression following check returns an error, what check does is it does something we call failure. and the failure is propagated up, and you can catch it. So here we are doing a check. If this check fails, then it will control flow will transfer to here. The error will be bound to E, and then you can do what you want with it here. So you can centralize you don't have to just return checks, you can catch them and do something with them. Now you might say, oh, this smells an awful lot like exception handling. Isn't this really exception handling? Well, no, it's not, because why this is fundamentally different from exception handling is that the control flow is explicit. You have a check here, and this check is saying, if this gets an error, transfer control to the innermost on fail block, or if there's no on fail block, to the function. So it is still, control flow is still explicit. You still know just by looking at the code how control can flow. So we use this in order to make, so we talk about commit, the other side of that is rollback. So when you, let's look at this example. Suppose I have an array of updates and I want in my transaction, I want to run all of these and all or nothing. So one of these updates may fail. So if this update, so this is going to return me an error. If this returns an error, I do check here. If this check fails, the transaction will catch it, and then the transaction will roll back. So when you fail out of a transaction block, that implies that you want to roll back. And similarly, if there's panicked, this would also roll back. And so the goal here is to ensure, one of the goals is to ensure that we have a compile time guarantee from the syntax and from compile time checking, we have a guarantee that every transaction, there's going to be a begin and a matching commit or rollback. And the way we do that is we say that when you exit the transaction block, you must do it in one of 4 ways. Firstly, here you've got a path. The control flow must pass through a commit. Commit doesn't exit the transaction block, but when control flow passes through the commit block, we know that the transaction has been terminated. You can exit it block by doing a check fail. So if this fails, this will exit the transaction block. If this fails, this will exit the transaction block, and that implies you roll back. And of course, at some point in running any of this code, you may get a panic, and that may cause the block to cause you to exit the block. And in that case, you will always get a rollback. And the other way we allow is you can have an explicit rollback statement. And if you have an explicit rollback statement, then that will also cause the cause the transaction to be rollback. So whatever you do, you've got an explicit check, you've got an explicit commit, or you've got a fail or a panic. In the commit case, the transaction will be ended with a commit. In the other cases, it will be ended by a rollback. So we guarantee at compile time that the transaction is properly bracketed. But note the rollbacks, I mentioned, we don't have transactional memory here. Rollback doesn't automatically restore Ballerina variables to previous values or anything like that. All it does is it communicates with, it tells the transaction manager to roll back. Another thing that our transaction support tries to make easy is retrying. So it's often the case with transactions that you can get an error that's transient, in the sense that if you retry it, it will go away. So you want to make it easy for people to do the right thing, which is to retry transactions. And the way this works is we have the retry keyword in front of transaction. What this does is it creates a retry manager object before starting the transaction. If the block fails with an error, then it calls the should retry method with that error. The retry manager then decides whether it wants to retry or not. And if it does, then it will retry that block. The retry manager can do whatever it wants. There's a default retry manager, which is what you get if you don't specify what retry manager. So you can put something in angle brackets here, saying giving the class the retry manager that you want. If you don't specify that, you get the default retry manager from the error module, and that has an argument. So you also pass parameters here. That gives you the parameters to new. So the default retry manager has a parameter that says how many times to retry, which defaults to 3. So this is exactly the same as saying calling the default retry manager from error with an argument of 3, and that will retry up to 3 times. So the should retry, it just increments the count of how many times you've done, and if you get to 3, it won't retry. It also looks at the type of the error. So some kinds of error it's useful to retry them. Some kinds of error, it's not a kind of error it's not a transient error, it's not going to help you to retry. So there's a distinct error type that is retryable, and your retry manager will look at that error type, see if it belongs to the retryable type. If it is, it will, and you haven't exceeded the number of retries, it will retry again. And this retry feature can actually be used independently of transaction. You can just retry a block, and it uses the same logic. We also try and do a little bit of static checking, and to make the code a little bit clearer, we have a transactional qualifier that can be applied to functions. The basic concept is that at compile time, we identify regions of the code as being transactional contexts. So within a transaction statement, the body of the transaction statement is a transactional context. And when you're in a transactional context, you are guaranteed at compile time that when that code executes, you will have a current transaction. So if you have a function that's declared as transactional, that means firstly, you can only call it within a transactional context. And secondly, that its body will be itself a transactional context. So here, this is transactional. So that means you can only call it within a transaction. And within a transactional function, we can call a transactional function. It's fine for do update to call bar. Bar requires a transaction. Do update guarantees that we have one. And you can also call a non-transactional function here. Now this is a little bit more interesting, because sometimes you often have the case where you're going to have something that's transaction aware, and it will go and call some other stuff, and then you have some other stuff that's not transactional, and you need to kind of pass through the transactionality without it being completely static. So what this means here, that's a Boolean expression that evaluates to true if you have a current transaction. And just as you remember, we had type narrowing. So I could say if foo is int, and within this body, we know that variable foo has type int. Similarly here, we know within this section here that transactional is true. So within this branch of the if, we know that we have a transactional context. And so here we could call bar, even though this function is transactional, we've checked here that we've got a transactional context. So it's okay to call bar here. Okay, let's talk about distributed transactions. So we've got these two interesting features. We've got transactions, we've got network, you've got network interaction features, services and clients. We want them to work together, and they do. So in language terms, there's not a lot to it. You can declare a remote or resource method of a service object as transactional, and you can declare a remote method of a client object as transactional. Mostly what's distributed transactions is mostly a matter of implementation. There's an awful lot that goes on under the covers to make it all work. So the basic concept is when I've been talking about current transaction in Ballerina, what I actually mean is it's a branch of a global transaction. So when I have a transaction statement, that creates a new global transaction, and the current transaction becomes the root branch of that transaction. You can then have client objects and listener objects that are transaction aware. Now, when a client or listener object transaction aware, there's got to be a protocol involved. If a client object, the client object needs to communicate with a remote system using some protocol, and they need to be able to associate the message that they're sending with a global transaction. And they also need to allow the Ballerina runtimes transaction manager to communicate with the transaction manager of the remote system. So there's got to be a protocol involved. So it doesn't, these distributed transactions aren't restricted to working just between two Ballerina programs. They can work between programs written in different languages, or from Ballerina to a database, so long as both sides understand the same protocol. So you can use both industry standard protocol XA. We also have something called the microtransaction protocol, which is Ballerina specific. And if you wanted other programs to play with that, then all you'd have to do is to implement the microtransaction protocol for whatever language you want to interact with Ballerina. So when you've got a transaction-aware client or listener, first thing it needs to do is there needs to be a protocol by which it can associate a network message with a global transaction, and also that the object or listener will need to interface with the Ballerina runtimes transaction manager. There's an API that the Ballerina transaction manager will have to expose to clients and listeners to enable them to to make everything work. And the language doesn't get into that. The language is just about allowing the application to delimit transactions. But under the surface, there's a lot more that needs to happen in order for this all to work. At the language level, the important thing to understand is that if you've got a transaction-aware listener and it receives a network message that says it's part of a transaction, part of a global transaction, that listener then has to create a new transaction branch and execute the service object in that transaction branch. So that service object will have a current transaction that is a branch of the global transaction. And it's similar to this. You can have named workers be. You can generally you want one transaction branch is one thread of control. If you have, because transactions is about managing concurrency. If you have two threads on the same branch, things are not going to work very well. So we can have, if you've got a transactional function, you can have a worker in it be transactional. And what that means is that the strand for this worker will have its own separate branch that will be joined to the branch on which this is executed. And that works very much like a distributed transaction. So this is then, if I have transactional here, I can, if I want, have transactional here, that'll start a new branch, and then I can then call a transactional function from that. So the final, I think this is the final bit of this is what we call commit rollback handlers. So often you have a case where you need to do something different depending on whether the transaction committed or was rolled back. Now you can, in theory, handle this by, so you do commit, that returns a value, which is an error or nil. You can see what it was, is it an error, is it not an error, and do something different based on the return value of commit. But your commit has to be, your commit's in one place in the transaction statement. And it's not very convenient to have to do everything that you need to do in the transaction statement. If you, for example, if you are, particularly because we don't have transactional memory, if there's something you want to undo, if the transaction was rolled back, you want that undo to be in the same place as the do. You don't want to have to put all that logic in the transaction statement. So that's one reason why this just testing the result of commit doesn't work. The other bigger reason is in a distributed transaction, the program, it's one program has the transaction statement, and another program may want to do something based on whether the transaction that was started here commits or not. And if you want to try and make that work, then you have to get into sort of sending messages, but it all gets very complicated. So instead, we have this way, we have this feature called commit and rollback handlers, where you can say, if you're in a transactional context, you can say, okay, when this function commits, run this function. This is a function. You say on commit, run this function. And what happens then is that so this is particularly useful. Imagine that update is being called from a transactional service method. So the transactional service method is not the thing that starts the transaction. There's another program that starts the transaction. It calls a service method. This service method then calls update function. And this function has no idea whether this commit is going to succeed or fail. But it can say, okay, if it commits, I want to send emails to somebody saying that it has committed. And what will happen then is that the program, the Ballerina program, that the transaction manager of the Ballerina program that initiated the transaction will send a message to the Ballerina program in which this function is running. And when, as part of the two-phase commit, when it knows that it's going to commit, it will then arrange, the transaction manager of this program will then arrange to call this function. So it's quite a simple thing, but it's really, really useful when you have distributed transactions. It's quite hard to, yes, sorry, go ahead. Okay, next bit. This is probably the most complicated thing in Ballerina, concurrency safety. So let's start off with the easiest aspect of it. So we have a lock statement, and the lock statement allows you to access mutable state from multiple strands running on separate threads with well-defined results. So the semantics is it's like an atomic section. It's like, in implementation terms, you can think of it as having a single global recursive lock. So there's one, you can think of it as having, so the naive implementation has one big lock. Whenever you enter the lock statement, you acquire that lock. When you exit it. In fact, that's not the way you're supposed to implement it. There's a bunch of papers in the literature that shows how you can, at compile time, you can analyze the code using the lock and split the one big lock up into lots of little locks. But from the point of view, what's important is with locking that the user has a simple model that they can reason with. So from the point of view of the user reasoning about locks, they can just understand it as there's being one lock, one global recursive lock that's acquired. So our main goal here is what I call service concurrency. When running services, we want to get decent performance, and we want to get decent safety, a decent level of safety. Decent performance means we've got to be able to have multiple threads. Listen, you can't just have one thread serving a listener. You've got to be able to have multiple threads serving things. And good enough safety means the one thing we really, really don't want is to have data races that are undetected. We don't want to be silently giving you wrong results. Ideally, what we want is to be able to check at runtime that you've done everything you should and that your program's perfect. But we can't always do that without getting very complicated. Or it's the same as with static typing. There's a trade-off between the safety you get and how complex the type system is. So we want a type system, a language that is relatively easy to use, but we really cannot allow you to have undetected data races, because for our target audience, that would create programs that just give the wrong answer, and it's very, very hard to debug. So the minimum is that the sort of decent level of safety is at least guarantee me a error at runtime. So the way we want it to work is that you've written a program, you've got some services. Those services have some resource methods, and the listener needs to be able to tell, is it safe to run those requests, run those services on separate threads or not. If it's not, then it can just fall back to executing all on one thread. If it is safe, then it can deploy. It can make use of multiple threads. And safe means it's not going to lead to undetected data races. So the program needs to be able to look at your service, look at your service objects, look at your resource methods and your remote methods, and be able to tell, is running these methods on separate threads going to lead to data? Is there a possibility that could lead to data races? So lock by itself it's part of the solution, but it's not enough, because you can't tell whether just lock by itself. There's no way for the program to tell, has the user locked when he should or when they should have. So we need a bit more than that. So the first part of what we need is we have this concept of an isolated function. Informally, you can think of an isolated function as being a function that's concurrency safe if its arguments are safe. So it's not unconditionally safe, but if you call it with the right arguments, then it's safe. So if you've got a function that's isolated, we allow you to access mutable state through the parameters, and we allow you to call functions that are isolated. You can't have an isolated function calling a non-isolated function, because a non-isolated function is basically a function where all bets are off. You have a function that's not declared isolated, you basically can do everything. It can do anything. You have no idea what it's going to do if it's called in multiple threads. So an isolated function is really, I think of it as a kind of, it means it's a well-behaved function. It's a function that stays in its lane. If you give it the right input, it will be well-behaved. So this is a concept that I don't know if you've heard of D. D is a language that written by somebody called Walter Bright, who wrote the first commercial C++ compiler, first native commercial C++ compiler, I should say. And it has this concept of pure functions. And pure functions are a little bit different. Pure functions are functions that only depend on their arguments, and that's not quite what we have here. Our concept of, so this is why we don't call it pure. It's a weaker concept than pure. It's similar to pure, but it's weaker, and it's targeted specifically at trying to help with the isolated, with the concurrency safety. Okay, so we have this concept of isolated function, which basically means it's a function that stays on its lane. If it stays in its lane, if you give it the right arguments, you can be sure that it will not lead to data races. So the next part is, so we've talked about immutable values, and in the language we use the word read only. In the syntax of the language we use the word read only to mean immutable. So we can actually have a type to which values belong only if they are immutable. So here we have a string array. So usually an array is mutable, but we can declare it to be immutable by using this type intersection operator. So read only and string. So you can think of this as saying the type of this is both an array of strings and it's read only. So that means it's an immutable array. So when you have a value that's declared as read only, that means you know at compile time, if I have a variable that is declared with this type, I know that it is immutable. And that means I can safely use it as the argument to a function. If I use it as the argument to a function, to an isolated function, then it's safe to, well, let me put it another way. If all the arguments to an isolated function are read-only, then it's safe to have that function run in a separate thread. So read-only is not about, it's very different from const in C, for example. If you have const in, well, I guess it came from C++ originally. So const in C is more like, is not saying something about the value. If I have a constant character star S in C, that is not saying that S is immutable. What it's saying is that this function won't modify S. That's completely different from what we're saying here. Types in Ballerina are describing values. So what we're saying in Ballerina, what we're saying here, if I'm passing in an array of strings, I'm saying the string that I'm passing in has the array that I'm passing in has the read-only bit set. It's guaranteed to be safe, and that's so don't get confused. It's easy to get confused because it's not trying to solve the same problem that constancy is, and so the semantics are quite different. So you'll remember that we could have this concept of read-only fields with tables. And what that means is that the field is immutable and the value is also immutable. So they're two separate things. When I have a field, if I have a field that has a value that's an array, I can assign a new value to the field, and I can also mutate the array. So they're two separate things here. Read-only means that you can't do either of them. Read-only means that the field is immutable, which means I can't assign a new value to the field. And it means that the value that is stored in the field is immutable, which means that I can't go mutate the array by changing the value that's stored in one of its members. And so when you have a key, when you have a key, a field that's representing a key, you need it to be immutable in that sense. You can't change the field, and you can't mutate the value of the field. So there are a lot of pieces here that come together to provide the concurrency safety, but they're useful independently. Okay, do we understand? Anybody got any questions about read-only? This is it's not actually very constant. All it means is values have you can think of it as every value having a read-only flag on it, and this just read-only is a type that matches a value if it has that bit set, and is just intersection. It's saying it must belong to this and it must belong to this. But this is different. This is not how most languages do it. Okay, so we talked about read-only values. We can now have a type that describes when a value is read-only. So we've got isolated functions. So we got a number of bits so far. We got this concept of a lock statement. We got this concept of an isolated function. And we've got concept of read-only values. And we've also got this concept of a read-only type, which is a way of describing at compile time when your value is going to be that you're describing at compile time that your value is going to be read-only. So so how does read-only work with? How does that help us with isolated? Okay, so imagine we're going to have a little type entry, which is a map adjacent, so that's mutable. And we're going to have a read-only map, which is a map of entries. So this is deep. And so in my program, I'm going to go load some JSON from somewhere from a file, say. So I go load my map from a file. Now this is interesting because I've got a variable m. It's final, which means that I can't change the variable itself. And it refers to something. It's got a pointer to something that is deeply immutable. So that nobody else, so because I've declared it as read-only and because I've declared it as final, this variable m is completely safe to access from multiple threads. There's nothing that can go wrong because it's final, and what it points to is not just read-only I'm guaranteed that it's read-only all the way down. So in my isolated function, it's perfectly fine to go access m. I can do that completely safely without endangering the safety of this function. Whereas if m wasn't final, then that wouldn't be safe because I could have some other function that would go, non-isolated function that go mutate it and it might not lock. Similarly, if it wasn't read-only, that also wouldn't be safe because there might be a shared reference into it that would go mutate it. But if I know that it's read-only, then my program at runtime will guarantee that nobody else can go in and mutate it. So you can think of isolated. Another way to think about isolated is that read-only is great for data. It tells you, so you've really got you can think of it as having three operations on storage. You've got read, and you've got write, and you've got execute. That's the three things you can do with stuff in memory. Read-only tells you about what happens when you do read and write. Read-only means you can read, and however many reads you do, you won't get something to your write. But read-only tells you nothing about what happens if you execute something. So read-only is just not a useful concept when it comes to functions. It's just uninformative function. You don't get to mutate code. So functions are immutable, but that doesn't actually tell you very much because what you do with a function typically is not read or write it, but execute it. What you want to know is what happens if I execute this function. That's what the listener needs. If it's got a bit of code, it's got the user is providing the listener with code in the resource method or remote method of the service, and the listener needs to look at that function and know that it's safe or not. Read-only doesn't help with that because read-only gives you no information about a function. This is why you need this separate isolated concept. Isolated is providing information about functions. Read-only is providing information about data, or isolated is providing information what happens when you execute things. Read-only is providing information about what happens when you read and write things.
James, question.
Yes.
Okay, so if you access, say for example, a map which is not read-only inside an isolated function, do you sort of get a compiler?
You'll get a compiler error. Yes, if you tried, if this wasn't declared as final,
I see.
Then you get an error here saying, sorry, you can't do that in an isolated function.
Okay.
Now, what's another thing you could do? So sometimes you'll get compile errors, but it's also possible to get runtime errors because remember that. Did I actually say that? So I should mention here that T and read only. So if I say something is read only and string, that's a subtype of string, and it's a subtype of read only. But that means, so this is another thing where we're trading off safety for simplicity. So you can actually cast away the const. So you could assign the RO map, this value, to a map just a map entry that wasn't read only. And if you did that and then tried to mutate it at runtime, you would get a runtime error. So you could stop that at compile time, but that would require you to. That would be really inconvenient from the point of view of writing programs. So we take a safety hit but you are guaranteed it is guaranteed that if you have a value that belongs to a read-only type, you cannot mutate it. It's not guaranteed that an attempt to do so maybe will be caught at compile time. It may only be caught at runtime, because you can assign the RO map to a map, and then you can then try and mutate it. And then it's like having a read-only bit on the value. And if you have a read-only bit on the value, you can try to mutate it. You'll get a sorry, you can't do that. Okay, so we've got, let's just, there's a long story here. So we've got lock, we've got isolated function, we've got read-only. So now we've seen how we combine read-only and isolated. Now, how do we combine read-only and lock? This is where it starts to get interesting. Well, this is where it starts to get even more complicated. So what we want is, so here we've got read-only variables. Yeah, so we've got completely immutable state. We can access this from an isolated function just because it's immutable. What we want to achieve is, but actually suppose I have mutable state here. I want the basic goal, what we're trying to achieve here is I want to be able to access mutable state by using lock. That's how these things need to combine together. Unfortunately, making these things work together is not trivial. So the basic concept is we have the concept of an isolated root, what I call an isolated root. So an isolated root is, you can think of it just being a little island where all the mutable state that's within that island has to go through. You can't get to it. There are no pointers into it from outside. You can only get into it through this root. And related to the concept of an isolated root is that we have an isolated expression. So an isolated expression is something where that we know that the value will be an isolated root. So for example, if I have a expression, so we only care about mutable state for this. So if I have an expression with a type that's read-only, that's an isolated root because there's no mutable state there, right? Another simple example is if I have an expression that constructs a new mutable value. So I have a construction that creates a tuple, a two-tuple. If E1 and E2 are isolated expressions, then this is an isolated expression. If this value is guaranteed to be isolated root, and this value is guaranteed to be an isolated root, that means there's no reference to it into them from outside. Then we know that this newly constructed array is also an isolated root. And slightly less obvious, so that's hopefully those two are both obvious. This is slightly less obvious, but true. If we have a function call, and this is actually what makes it all work. If we have a function call, and this function is an isolated function, and these two expressions are isolated expressions, then this function call expression is also isolated. In other words, if this value is known to be an isolated root, if we know that this value is an isolated root, and we know that this value is an isolated root, and we know that this function is an isolated function, then the value we get back from calling the isolated function will also be an isolated root. You might have to think about it, it may not be, but if you think about it, but you will see that that is also true. Okay, so how do we use this to combine isolated functions and lock? So this is its own little journey here. So we have, the way this works is we can have variables declared as isolated. And when you have a variable that's declared as isolated, this is a module level variable, and we've declared the variable as isolated. It's not read-only, it's mutable. We've declared that is isolated. And when you have an isolated module level variable, first of all, you're not allowed to have it be public. Second, the compiler will check that this variable is only ever accessed within a lock statement. So if you have a variable, your modular variable is declared as isolated, you can only access it within lock. So here we've got our isolated modular level variable. We've got two isolated functions. that are mutating it. And because we know what the semantics of lock are, it's one global lock. So we can, because we know that stack is only ever accessed within a lock, we can actually say, okay, it's actually okay for this isolated function to access this global mutable state, because I know that this state is only ever going to be accessed within a lock, which means that you're not going to get any data races from doing so. So it's a little bit more, so the rules for, so there are some rules for what you can do. So if you access, so within a lock statement, if you access an isolated variable, you are constrained in what you can do in that lock statement. You can't access two, for example, if you have two isolated variables, you can't access both of them in one lock statement, because then they could get tangled up and they wouldn't be isolated anymore. You also have to, you're also constrained in how you think of it. Basically, what you need to ensure is that, so we have the invariant that this isolated variable is its own root. So you have to ensure in the lock statement that invariant is maintained. And that means within the lock statement, you're restricted in what you can transfer in and transfer out. Basically, you have to transfer in and transfer out any other isolated things. If I transfer in an isolated things, I can glom it on here. But if I go transfer in some other non-isolated state and start stucking it in, then it's not going to maintain that invariant. So there are some rules that you have to follow when you're using a lock statement to access an isolated variable. There are some rules you have to follow in order to ensure that the invariant of the isolated variable being isolated root is maintained. Okay, so now we've got isolated functions, we've got lock, we've got read only, and we can put all these together, and this allows us to have isolated functions that actually manipulate mutable state in a safe way. So we're not there yet. We're getting there. We're nearly there. So methods. We can have isolated. So we're dealing with what we're interested primarily in is service concurrency, which means we're interested in being able to run remote methods and resource methods of service objects concurrently. So you can declare a resource method or a remote method of a service object as isolated. And what that means is just like an isolated function where self is treated as a parameter. So when you have an isolated method, what that means is if your object is safe, if you can think of self itself, you can just think of as being an implicit parameter that's passed through. It's just a method calls that really, you can think of them just being a fancy syntax for. You can think of self as just being an implicit parameter. Basically, when you do x dot y, you're just passing in that x as when I do x dot foo, I'm just passing in x as a parameter. So if you apply the isolated function concept to methods, what that gives you is that self is basically like a parameter. Unfortunately, this isn't enough. This isn't enough to get service concurrency, because if you think about when a listener makes a call, think about a listener making a call to a service object. It's the listener that creates the parameters. So the listener gets a network message. The listener is responsible for turning that message into a bunch of parameters that it passes to the service object. So the listener is in control of the parameters. It can make sure that they are concurrency safe. On the other hand, it's not in control of the service object. The service object is provided by the user, and the service object can have mutable state. So just this concept of an isolated method is not enough for the listener to be able to do what we want to do. We need one more thing. And that one more thing we need is isolated objects. So you can think of, so there's a parallel between objects and modules. A module is very much like the right way to think of a module like an object, or an object like a module. You can think of a module as being like an object, and you can think of the fields, or you can think of the variables of the module as being like fields of the object. So an isolated object is like a module where all the module level variables are isolated. So let's look at it. It'll be easier with an example. Suppose I'm creating, so I have created an isolated object by having an isolated class. So when I have an isolated class, basically all the variables of the class are like isolated variables of a module from the point of view of the, so first of all, they have to be, you can't have any public state, it has to be private. Just as you can't have public isolated module level variables, all the members of an isolated class have to be private. So all these private members of a class, these private fields of a class get treated, have to obey the same rules that isolated module level variables obey. So if we look at this example, so this is as an isolated class. So the rules that apply to this, so first of all, this variable has to be private. So this field rather has to be private. And secondly, we apply same rule, the rules that we apply to module level functions as vis-a-vis isolated module level variables apply to methods of the isolated class when they're accessing fields. So this has to lock. You can actually think of it as perhaps an easier way to think of it is that self becomes an isolated variable. So this, you can access self basically just like an isolated variable. So whenever you access self, you have to lock. Is the simple way to think about it. Just as in the module level case, in the module case, when you access an isolated variable, you have to do it within a lock. So in the isolated object case, when you access a field, when you access self, when you access a field, which you do via self, you have to lock. So we can see that this object here is safe. So it's got state, yes, it's got mutable state, but whenever that mutable state is accessed, it's done within a lock. So yes. Okay, so this is actually what we need. So this is what we need to make service. This is what we need to make service objects work, because if your service object is isolated, and so that the isolated, so there's a difference. So isolated for the object and isolated for the method are different things. Isolated for the object is talking about the variable, the fields of the class. Are they always protected with lock? So that's what a listener needs in order to be able to call service methods on, to be able to call methods on service objects concurrently. So if that service object is isolated, then it's safe to make calls, concurrent calls on that object. And one very simple way that an isolated service object can be isolated is not having any, if it doesn't have any fields, if it just has methods and no fields, then it has no mutable state, so it's automatically isolated. Now at this point, you're probably thinking, this seems a little bit complicated. And how the hell is anybody supposed to figure out how this works? Well, the answer is, most of the time you don't need to worry about it because the compiler can figure it out for you. It can infer isolated. So in your typical Ballerina application that that the average user is writing, you've got a single module that does the work, and it calls a bunch of library modules. And within a single module, we can actually infer. The compiler can infer when something is isolated. It can infer isolated qualifiers for objects, for variables, and for functions. And one very simple case of this is that when you have a service object without mutable fields, then that is automatically isolated. So so that the user doesn't really have to understand about all this isolated stuff. All they really need to understand is this. They need to understand that if they want to have things work concurrently, they need to better apply lock to stuff that's potentially accessed from multiple threads. So we have this very simple lock primitive, and all the user has to do is, they don't have to write this isolate, they don't have to write this, they don't have to write this. What they do have to do is write lock. They have to know, okay, so this is a kind of, if you think of this as being a service object, if you want to have that service object, if we want to have multiple threads using this single service object, well, and you've got mutable state, you've got to lock it. There's no getting away from that. But the compiler can help. The compiler can say, look, if you just use the lock here to access this private state, I could run this concurrently for you. So the point of this whole story is we have this quite complicated system, but what it gives you at the end of the day is that it gives you a decent level of safety. It gives you a decent level of performance, and it gives it puts a moderate burden on the application developer. They have to use lock, but they don't have to use lock. If they don't use lock, then the program will work correctly, but it just won't be concurrent.